Okay, I guess we'll get started. So welcome to this second presentation now on gRPC and LabVIEW. I'm going to talk a little bit about what gRPC is, what NI is doing with gRPC, including support for LabVIEW, and kind of what that is shaping up to be like, a little bit of our roadmap, and then ways that you can help us kind of drive the direction of our use of gRPC across NI and specifically for LabVIEW itself. So let's get right into it. So what is gRPC? It's another essentially remote procedure call. Technically today, the G in gRPC doesn't stand for anything. It used to stand for Google, who originally created it. It was initially released to the public in 2015, but it evolved internally at Google for quite a while. They had a thing called Stubby that they used for their own internal communication between their systems. And then as that matured and became happy with it, they made it public. And what they did essentially was try and build an RPC system that works well basically with modern internet infrastructure. And so gRPC is based on HTTP2, which is essentially the evolution of HTTP. And the internet essentially is designed around support of HTTP and HTTP2. So by building it on top of that, they have really easy integration with infrastructure that is in place across the internet. And it was designed essentially to build services to do communication in backends and more so today front ends as well. So that work happened, and then they essentially released it to the public in 2015, like I said, and then they also released it to basically an open source governing foundation. And so now it's part of the Cloud Native Computing Foundation. It's not technically owned by Google anymore. Although Google plays a fairly large role in the evolution of gRPC, it's technically under the ownership of the Cloud Native Computing Foundation. gRPC was designed with several key principles. I kind of put a little star here next to the ones that were the most interesting to us when we were looking for a technology to choose. General purpose and performant. So we wanted something that worked well for all kinds of scenarios. We wanted it to be interoperable and reach a whole bunch of things. Today, we see more and more heterogeneous deployed systems out there that are using many programming languages, many types of systems, many OSs. And so we wanted to make sure that what we chose would work really well in all of these scenarios. We really like this idea of streaming. So especially for things that we do, we have lots of data that we want to move around, and having a model that can actually stream the data, think of like a continuous data acquisition or things like that. That was very important to us, and gRPC has a really nice support for that as well. And you can see a bunch of other things that gRPC supports as well, like cancellation and timeouts. So you can have a system that's running when something stops working. There's a good model in place to know that it's timed out, and you can also like cancel things if you no longer need them. And just a lot of really interesting ways of designing gRPC that they kind of put into the foundations of it. Like I mentioned, they chose HTTP2 as the transport. And the motivations for that were really this easy, use of common internet infrastructure, things like load balancers and reverse proxies, firewalls and gateways and things like that can all understand what is going on, what's being communicated. gRPC looks like an HTTP call, like where it has a route, so like the URL. It has headers that basically describe what's going on, and then it has a body, which is the data, and that's very much similar to what you would see in any HTTP communication. So all those things work really well. And it supports, this again, it's this notion of it's being very fast. So it uses a binary format to be very efficient in its use of the network. And HTTP2 has this notion of streams internally. So when you open an HTTP2 connection, you can actually send multiple things back and forth across that connection, these notion of these streams. And so gRPC uses those streams for its communication. So one connection that you make, you can actually send multiple, multiple connections simultaneously. So you can, as a client, open one connection, send many requests out, get results back, do many streams at the same time, and everything works really nicely. Like I mentioned, it uses protocol buffers, which is a binary, basically encoding of data. It's very efficient. It's very extensible. You can version it, and you can really do a lot with it. And one thing we'll talk about too is this: you use this IDL to define the communication. So you can you basically define a very strict contract that you're going to use for communication. And that works well then for different languages that are strongly typed, languages that are loosely typed, things like that all work really well with gRPC. Some of these key features, like I mentioned, so it has this notion of you basically make a simple service definition. It's a fairly easy language to define what you want to do for communication. With that, you can then support just about every language that's interesting these days. There's official support for 11 different languages, but there's a lot more other languages that are supported as well by different groups that are interested in supporting it, or the language owners as well. So you'll see just about any language you can think of likely has gRPC support these days, and it's really nice. A lot of languages are built on top of a base C implementation that's provided by the core gRPC. And then other ones just write it from scratch in the language itself. Like I mentioned, it's cross-platform. So we use it on a variety of platforms: Windows, Linux, Mac, Linux RT. It works well on all of those. Because it's built on, it's designed for the internet, it needs to be secure, it needs to be encrypted. So you can use authentication and encryption with it. So just like HTTP, you can use HTTPS instead, where you use a certificate-based system to encrypt the communication that's happening between the client and the server. It also supports this notion of what they call mutual TLS, where both the client and the server provide a certificate. And what that lets you do is essentially verify both the client and the server are trusted. And they call it essentially this like zero trust computing. You'll see that becoming more and more prevalent these days, which basically allows you to guarantee that both the client and the server are who they say they are and can be trusted. And so gRPC supports that as well. You can also use things like ways to authorize users, things like that. Like I mentioned, there's it's like an HTTP call where you can put stuff in the headers, and that's a typical way you can do things like verify users. So you can do authorization as well as securing the connection. You can make standard calls. So a urinary call, basically send a request, get a response back. Typical like function call style remote procedure call. And then this notion of streaming, which has been very interesting to us to enable us to do much more performant communication of large data or long-lived data. And again, like I mentioned, this notion of cancellation and timeouts as well is a really nice feature to have to make sure your system can be robust when deployed. Interestingly enough, so again, gRPC today essentially has, I would say, the largest mindshare of companies and people building tools looking at trying to do some kind of remote procedure call. HTTP REST style communication and gRPC as a binary style communication are essentially the dominant forms now of basically communication across the network. And you'll see that more and more. Major companies, Microsoft, Google, Amazon, Netflix, people like that are all using gRPC today as their basically tool of choice for communication between their services. And one of the nice things about when you adopt gRPC is you can take advantage of a lot of things that are out in the general software industry. So this is a smattering. There's this awesome gRPC GitHub repo that basically lists all these things, and this is a smattering of the kind of things that are available for you to do things from, using lots of tools, lots of good test infrastructure, lots of interactive tools for working with gRPC. So that's one of the really strong advantages of gRPC, is that not only is there stuff that we make, stuff that a core, like say, people in industry would make, you could basically take advantage of the entire software industry. All the big players are investing in this technology. So let's look at gRPC real quick, kind of talking about like where you start. Like I mentioned, there's this proto file that you create. It's just a text file that basically defines the contract that you want to use for communication. And so, basically saying we're using Proto 3 syntax. So the protobuf, this is now the third kind of revision of the proto syntax to add support for gRPC. So you basically define that. You can provide a package for your thing, and then namespaces. These options, when you see options like that, are language-specific callouts. And so you can do things like say, well, when C# code is generated, use this namespace, or when you're generating Go code or JavaScript, you can add additional options as well. And so you'll see those for each language has a variety of different options that you could choose to basically augment your generated code with. And then it's a very simple, you define a service. So basically it's a collection of methods that you want to use. And then you basically define those methods. Every method is marked as like an RPC, the name of the RPC call, and then all RPCs take a request object and return a response object as a reply. It's always one request, returns one response, but those requests and responses are essentially a collection of fields. And so you can think of them as like a LabVIEW cluster. And so you define those, you get a request object, and then you get your reply object back. The key thing here is when you're defining these, you define them with both the name, the type, and then a ordinal value that basically specifies where it is in the gRPC, which one is it. And that lets you evolve it over time. There's a few things that are interesting about the gRPC communication. One is when you send a request out, you don't have to provide all of the parameters on the wire. You can skip some that are the default value, and it's very common to have a more compact transmission. And there could be actually ones that you don't understand. So as things evolve, there might be things in the request or response that are like old, or things that you don't understand. So you should make sure that you can support that as well. So when you have language support, you'll see that it's supported with unknown fields. So that lets you basically evolve these requests and response over time. And so it's important to make sure you know what the ordinals are, to never use redundant ones. That's actually an error. And to never change what one means. So if you say the name is 1 and you want to change it to be something else, don't ever reuse the number 1 again. Pick a different number. That way, when things are sending and receiving the messages, there will be no confusion. gRPC on that proto-def supports all kinds of data types, all the standard ones you think of. So for numerics, there's actually several integer types. They have these notions of ints and signed ints and things like that, which are actually like a compressed version of an integer. So if you would say, for instance, want to send over protobuf just an int 1, it would actually only require 2 bytes. The first byte is basically saying what it is. It's an integer. And then the second byte is actually the integer itself as the number 1. It doesn't actually use 4 bytes, even though it's represented as a 32-bit integer. It doesn't have to use that much data. It won't. And then there's floating point values as well, floats and doubles. There are actually integers that are fixed size. So if that encoding gets slow because you have a lot of integers, or they typically are big, you can declare them as fixed size as well. There's Boolean type strings, numerics, enums. So you can do enumerations in gRPC, and They basically can have repeated fields. They're always integer-based enums. That somewhat limits it, but you can do a lot with that. And of course, you can then nest your messages. So if you have a message, it can contain nested messages. So you have common sets of information. You can do that as well. And so that, like in LabVIEW, that would be just having a nested cluster. And then you can take basically any of those numeric types and build an array of it. And so you can have an array of numerics, array of Booleans, or whatever you want, or array of messages as well. And that lets you build very, expressive data types out of this. And there's a couple other unique things. There's this notion of a one of, which is a union type. And so you can say, this message is one of the following things. And that just gives some language hinting to say, you should only ever set or get one of those. So it's basically a way to do a union of data. And then there's this notion of this any type. So the any type is actually not built into protobuf. It's what they call a well-known type. And so they wanted a variant type that all the languages could understand. And so they built this one type called any. It's really just a message that has two fields, that has a string that is the type, and then it has a bytes array, which is the embedded proto of the actual value. And that's called the any type. And so basically lets you make variants and then have a good API to unpack and pack up a variant. And so with that, you can really do a whole lot of things, have a really good expressive set of messages that you're sending back and forth. So this is, again, what it looks like. What you do is on the server side, you basically build a server and you define that. And then you can, you just give whoever needs as a client, you give them the proto file, and then they can take any language they want, and they can use the proto generator or protobuf support, gRPC support within that language to generate the code for it. You as the author of the server, you can, you don't have to give them more than the proto file. So whatever OS they're on, whatever language they're using, you don't have to care, essentially. You just give them the proto file and they can get up and running. A couple quick notes here, like on security, like I mentioned, it uses OpenSSL as its encryption layer. So you use, it's called TLSS or, HTTPS, any of those things is really the same thing. You can use a certificate. You can use self-signed certificates. So you can basically, kind of create your own certificates and then keep that on the server and then give your public certificate to the clients. Or you can use one of the standard root authorities to create your certificates for you. Makes it a little easier on clients, but you can kind of do it either way. And then, like I mentioned, there's this notion of authorization. And so with that, what that means is essentially you can put things in the connection or per call that identifies the client. So you can say, here's an API key. You see that a lot like HTTPS communication, you have to put an API key into the header for the server to respond to your request. You can do things like put the client identity information in there, so you can have, say, okay, certain kinds of clients can call certain kinds of methods. And that's all well supported then inside of gRPC as well. So you can kind of think of it as, somewhat of a binary form of HTTP REST style communication with some more additions as well. But the kinds of things you would do with HTTP, you can likely do with gRPC. Versioning, I mentioned this a little bit, but you can essentially update your contract over time without breaking existing clients. Like you said, you can obviously you can add new fields to a message. So if you want to need more information, you can just add new fields with new IDs, and then new clients can fill out that information. Old clients won't break the serialization, deserialization. The understanding of what's in the messages can be preserved. The server has to be, aware that not all fields might be filled in, and they support that. But in general, that's supported well. You can also mark existing fields as deprecated. You can technically remove fields that would break clients who want to recompile, but existing precompiled clients who aren't regenerating from protofile would not break. They would just become unknown fields on the server side. And of course, you can add new methods to your service. So if you want to add a version 2 of a method, that's fine. You can also create new service interfaces as well, and that will not break existing usages. One thing that was very important to us was performance. And so we wanted to take a look at and say, what is the performance? Do we think it can meet the needs of remote use cases that we see for both what a LabVIEW case would be, and then for other cases that we want to start supporting? And so we ran a whole bunch of benchmarks. A couple of key ones here I kind of underlined. And so we wanted to see, like, what is the performance of just sending data over? So like, how many megabytes per second can you stream data? And it's actually really good over a 1 gigabit network. A 1 gigabit network has a theoretical maximum throughput of 120 megabytes per second. And gRPC itself can do 111 megabytes per second of just the payload data. So all the other like overheads and stuff are not included in that number. So you can get within greater than 90% of the theoretical maximum achieved with gRPC with your payload data, and that scales too. So we looked at like a 10 gigabit network. A 10 gigabit network has a theoretical maximum about 1.2 gigabytes per second of data, and so we got about just over 1.1 gigabytes per second. And that's a direct connection. But if you're switched on it as well, that would have basically the same megabytes per second. And then also looking at like things like latency. So how long does a call take? And we're able to actually get latency numbers down to around over a 10 gigabit network, close to about 50 microseconds on average for a call. That's a round trip call. So basically 25 microseconds to send and then 25 to receive. And so that's actually really good. So if you are concerned about latency and throughput, gRPC is an excellent choice because it has really good performance. It's really hard to beat those numbers kind of on your own. So if you wanted to do better, you can maybe get just a tiny bit better, but you lose out on all the niceties once you start adding things like security support, all the other things that gRPC puts on top of it. You're likely probably to do worse than what gRPC can do. Like I mentioned, interactive use, that's something that people like to see. There's lots of tools out there that enable interactive use. There's a couple good ones that we will show today. One is called RPC, which lets you kind of interactively construct a call and then make the call and then see the results. And then things too like Jupyter Notebooks. gRPC works really well in Jupyter Notebooks. So if you want to like do interactive Python style development, that works really nicely with gRPC. And of course, new is a LabVIEW VI. LabVIEW VIs are great tools for interactive use of different things. And so it's really easy with our LabVIEW support to just use your VIs to experiment with calling gRPC methods. So what are we doing with gRPC at National Instruments? There's a couple key ones that we are really pushing on right now. One is called gRPC device. And what we're doing there is essentially putting a gRPC remote API on our device drivers. So the driver API for all of our devices. We're starting with the most popular ones that are demanded, and basically enabling remote calls of our devices. And so what we're doing there is essentially as an open source project, we're building a gRPC server that you can put on any of our OSs that support our devices, and then basically get remote access to that hardware. And then what we're here really talking about new is the support in LabVIEW. And so we really want to make sure that LabVIEW can participate in this ecosystem. And so we're basically taking on this work of building gRPC support as for both servers and clients written in LabVIEW. And we're doing that again on GitHub as an open source project. And so for us, this is a nice way to participate in this ecosystem. gRPC is generally an open source ecosystem, so we thought it would be important to follow that along. And so we now have that as well for LabVIEW. And then it's an evolving project. And we're also looking for to use gRPC wherever we see this kind of need for remote access to APIs. We want to start having a good remote access support for our software products and our hardware, that works on basically any kind of client. As we see these kind of heterogeneous systems out there in multiple languages, we want to have a way to basically make all of our software and hardware easily reachable by basically wherever you want to be as a user. So let's take a quick look at gRPC device. That, again, like I mentioned, is an open source project. It's being developed basically kind of incrementally. What we do is we pick a device family like NIDMM or scope. We build out the support for the gRPC API for that, and then we release it on GitHub. And so we don't have a yearly release. We're not tied to a hardware release or anything like that. We just release this support every time we have a new device family ready to go. And so we've released it 6 or 7 times this year already, and we're still building on to get all of the devices supported. Again, it's on GitHub, so you can go get the source, compile it for, if you have a specific like Linux distribution that we haven't supported yet or something like that, you can build it yourself. It's pretty easy to build. It's MIT licensed, so it's essentially free to use and free to modify. If you need to fork it and add some new capabilities, that's something you can do as well. These APIs mirror our C API, so if you know how to use that API, you can look up documentation on it. Calling the gRPC API is very much like that. And then eventually what we're going to do once we have all everything in place, we're intending to basically fast follow driver updates. So as we release a new version of our drivers, hopefully soon after, we'll see the gRPC support for any new features that have been added to that driver get added as well. Finally, LabVIEW support. So this is one we've been working on for a little while now. And what we're trying to do is develop this kind of core gRPC support to enable all the standard uses of gRPC. So the things that you would see in other languages, make sure that LabVIEW essentially becomes a first-class citizen in the gRPC ecosystem. So we want to make sure that everything that you can do is well supported in a way that LabVIEW users would expect, and basically be feature complete. So again, we're developing this as an open source project. It's on GitHub. It's MIT licensed, so it's free to use. And we do certainly appreciate community involvement. One of the things we really wanted to do is put it on GitHub, and then encourage the community to provide feedback on it, to make pull requests. We've already had several people outside of NI contributing to it. That's been very much appreciated. We're all kind of doing good work there. So, and again, we want to release it essentially when there's stuff that's stable and interesting to use. And so we're not going to tie it to a LabVIEW release or anything like that. We'll release it when there's new capability that's ready to be used. So for LabVIEW, again, the first thing we did was server support. So we wanted to do a fully featured gRPC server that can do standard RPC calls and support streaming as well. So you can do client streaming, server streaming, bidirectional streaming, and then let you handle it in different ways. And so we use events to signal when an RPC is available. And there's different models you can use to handle those events. You can do a synchronous model where you basically have a single event loop. We have different ways of doing asynchronous, and we also allow you to do things like have your own kind of custom dispatching. So if you want to handle gRPC events by dispatching them to actors that you might have as part of your system or things like that, we tried to make it really easy for you to kind of integrate the gRPC support in a way that makes sense for your kind of overall application. And then we also want to make sure we have good client support. So we make sure that any gRPC API that's out there available to use, we have the right support inside of LabVIEW, so you can call that API. And then something else that has come up as requests is kind of going below gRPC and just directly working with the protobuf. And so if you want to like serialize to protobuf or deserialize, we have a couple of models for doing that as well. This is kind of in early stages, so that's something we're still working on, but can be used today. So let's look at real quick what it looks like to do a LabVIEW server and then call that from a variety of languages. So what you do in LabVIEW, so you can go to GitHub. If you go here, you can see this is the gRPC LabVIEW page. If you go to releases, you can see we've done 15 so far. And you can get the latest version. And today, this include basically if you download it, it's packages that you can then install into LabVIEW, and that will give you the support you need in VI Live, and then also something in the LabVIEW Tools menu. So if you want to generate a server, you can go to Tools and say you want to open the generator. And then what you do is you pick your proto file. So you just open that proto file. This is the hello world is a standard one. That's like the default example for each language. So if you go to the gRPC website, they'll use this one as their standard example. And then you pick what project to generate into. And our goal for this was to essentially let you generate into a project, and we'll generate it into a library that you name it. And then as you make changes to the proto file, you can rerun the code generator, and the code generator will then just change the things that have changed in the proto file. So if you add a new field to a message or add a new method, it'll get added to your project, but we're not going to change anything else, and we won't delete the code that you added. And so our intention is that you can do this over and over again on the same project. And safely updated. If you delete things like messages and things like that, what will happen is the support will go away, but the code that you wrote around it will essentially be left behind, and it'll likely be then broken. So you create that, you can tell what you want to generate, a server or a client, and then you just run this, and it'll basically parse the proto file and either script from new or update an existing implementation. So this is going to do it from new. But so you shouldn't be concerned with running this tool over and over again into a project that you have other things as well. We're only going to modify the things that were created by the scripting tool itself. And so there you go. You basically get this server, and it essentially creates a class then that is your server implementation. And it has a VI that's your main to run the server. These inputs are basically where you can specify the encryption. And so if you want to have an encrypted connection, you can specify your certificate here, your key file. If you don't specify those, it runs as an unencrypted connection. And so it's essentially, easy to see binary data that's not secure. And then you give it the address that you want it to connect to. And you can basically give it, say, localhost, and that means it only listens locally, or you can say, I want anyone to access this server, and you define the port that you're listening on. So if you give it a port number there, it'll use that port by default. You can also specify 0 for the port, and then it'll pick a random port that's free on the system. So if you want to just use whatever port's available and then somehow publish that port number, you can do that as well. And we'll return back here what port we're actually listening on. And so what we're going to do is fill this hello world in and run it from Python. So I'm going to use the synchronous model because it's just kind of quick and easy. But we have documented on our website then the different ways to do this. And so in this case, there's a single VI that basically implements everything. And you have an event structure that handles the different RPC methods. And so you can say add an event case, and you'll see the different RPC methods here. In this case, there's only one. It's called say hello. And then what we do, we give you this ID that represents this call. And so you can then use that ID to get the request and then set the response. You can also use that ID and dispatch it somewhere else. So you don't have to do all the work within this event case. You're free to do what you want with it, and the ID will remain valid, and the method will be basically open in the pending state until you actually set the response. And the event has been, the method has been completed, and then the client will receive the response. And then for each RPC method here, we generate you basically VIs to get the request and set the response. And so that's been typed to what was specified. And so I get the response. These are all, like I said, they're all clusters. So I can just unbundle that. If you look at this proto file, basically you say hello, you pass in your name, and then the server will respond with a message. And so we're going to get the string that the user specified as their name. We're going to build a string out of that. And we're going to wire that in a second, and we'll say hello. And we'll say from LabVIEW. And then we'll just bundle that up. And wire it in. Oops. Fix it. All right. So now we have our server implemented. Just that easy. And if I go here and I run it, server is now running, waiting for connections. And then I can go over to say like Python. You'll see this Python is creating a connection, a channel to this. And then it's going to pass in demo as the name. And if I run this, you'll see hello demo from LabVIEW. So it called the RPC method. LabVIEw received the event, did whatever it wanted, and then returned the response to the client. And again, this will then work from any client language. And then there's like these tools, interactive tools. So like ORPC, you can do something very similar. So you can see it, again, it can parse it. We're gonna go to localhost. And our name can be, Chris. And if I run this, you'll see it get a response back. And one interesting thing too that ORPC is using is basically a JSON form of the gRPC call. And so there's basically a well-defined JSON syntax that matches the gRPC calls. And so there's tools out there that you can use to basically do like logging and playback of gRPC calls. And those tools can store the calls as JSON. So you can basically make it human readable as well. Interesting things like that. You can use it for like logging purposes or writing tests, things like that. If you want to test your server, there's a lot of nice testing tools where you can basically define a JSON recipe for the communication and then play that into the server and then check the results back. And you can check, make sure you got all the right messages back. So there's lots of good tools like that as well for doing the communication. Stop my server. And a quick look at our roadmap. So we're not calling this a 1.0 yet. We want to make sure that we have essentially something that we can guarantee compatibility with. And so we want to finish all the data type support, finish the client support and protobuf, and then we want to make sure the generated API everyone's happy with. So like, what are the names we use? What are the names of the VIs we use? How's the project laid out? Things like that. Once we're happy with that, we're going to call it a 1.0. And our goal then, once we hit 1.0, is to maintain backwards compatibility. So as you guys develop things on top of it, you know that if you get a new version of the tool, the work you've done already will be compatible. Today, essentially, our kind of under the hood implementation, we try and make backwards compatible already. So it's unlikely that something would break. What could break though is essentially, so if you have a gRPC server and we do a bug fix in the underlying implementation, you can get that bug fix and it'll likely still work. What we're not really claiming compatibility yet is if we regenerate the client or the server over and over again, we might have changed some names of things. So there might be a little work for you to do to kind of uptake a new set of generated wrapper code for the server or the client. So that's something to be aware of. We're trying to really hard to get that all straightened up, make sure we're really happy with it. One thing we'd like to get feedback from you guys as well is this something we should ship with LabVIEW? Should we just maintain it as an open source project on GitHub? Should we just publish the packages? What would you guys like to see as far as how we should, once we hit 1.0, how would you like to see it delivered to you? Real quick, so we're a little short on time here. I want to show you a couple other things that we're working on, ways to do essentially direct protobuf serialization. And so this is something that's come up. People just wanting to use protobuf as a way to essentially as a flatten, unflatten from string replacement that can work with other languages, as well as ways of working with, like, say, the any type or things like that, things that are more dynamic inside of gRPC itself. So we have a couple things that I'm going to show you here. This one for protobuf serialization, where you use a protobuf to define your message and then be able to pack and unpack it directly. And then one that actually uses what we call a builder syntax to basically build a binary protobuf without actually having a protofile, and then be able to unpack that, again, with no protofile defined. So I can show you that real quick. And again, this is kind of where it's kind of more just the low-level implementation. And so something that works today, but we don't think it's really quite ready yet. It's, you're defining this metadata here, kind of shouldn't have to do that. So we want to basically let you code generate, just like you did a server and stuff like that, a API to do this very easily with higher level wrappers around this underlying code. But if you have a need today, like I said, you could use it. And as we add the higher level APIs, you can make use of those. It's not going to break your existing things or won't break already serialized things, because again, the protofile underneath the hood is well defined, and we're following that convention. And so in this case, what we're doing is, let's see here, we basically just create this session. What we use that for is, because protofiles can be recursive and have nested definitions of things, when we create a session and we register our metadata and stuff like that, we basically build a model inside of the underlying server code to make it very efficient then to read and write those protofiles. And so once you have that created, you can call pack to buffer, and what that will do is you wire in a cluster that matches whatever you define here, and it'll return you a byte array that's packed as protobuf, that information. And then you can unpack it. So same thing. And what you do is you basically pass the name in this low-level implementation. You pass the name of the thing you're sending. And so if you run this, you'll see from panel that we did pack in 67, and then we read out and we got 67 back. So they are equal to each other. So it's a simple way, but if you're looking for something that's a little more universal for like flatten, unflatten from string, this is something you can look at. And again, this takes a protofile by default. So you'll think of it as you'll define a protofile so that other languages can use it. And then we also have this very generic, we call direct field manipulation. So what you do here is essentially you can say begin building, and then you just can keep adding data to it. And so in this case, we're adding like an int and then a float and then a double, an array of floats and a string and a Boolean. And you just give them all the different protobuf IDs. And then when you call build, it'll return a buffer. Again, this byte array that represents that protobuf. And then you can turn around and ask us to unpack all the fields. We'll parse the protofile. And then you can ask for each field with the corresponding type and get the value back. And so you have to know what you pass, what, each one was, or you'll get an error back if it doesn't match. And then you can, use that as a very generic way to go field by field, packing and unpacking. So I can run that. and you'll see just a quick example. All the values are read back out, written to buffers and read back out. So this again lets you have a very efficient way to basically universally pack up data suitable for sending over the network, or just saving to a file or whatever, and then knowing that you can do the same thing in any other language to get access to that data. And then finally, like I said, there's all kinds of ways that you can help if you're interested in this. Again, giving us feedback on the generated code. What are the, do you like the names we chose? Do you like the way we structured the server? Are there things we should change about it? If you want to have feedback on that, you can file an issue on the GitHub repo, and we'll take a look at it. Documentation is pretty sparse right now. So if you are interested, adding documentation is always welcome. Creating good examples is something we would love to see more of happen. Right now we have very limited examples. Expanding our test suite, which is pretty lacking right now. All those kinds of things are fairly easy things you can do, without really getting into the code. And then if you want to get into the code, looking at improving the error handling, especially in the scripting cases. There's things that prop up from time to time that are errors. The error we return right now is pretty cryptic. You usually need help understanding it. Again, improving the way we do scripting, we welcome that as well. And then obviously just become a user of it, and then file bug reports and any feature requests you might have. That kind of stuff, just go ahead and put on the GitHub repo. If there's something you'd like to see happen, just file it. Even though it may not happen for a while, we'd love to get the feedback on it. With that, we have a few minutes. I think I'm technically over on what we're supposed to do, but if there's any quick questions, I haven't seen the chat at all. So if anyone has any questions, this is an interesting one, complex data. Something we could definitely do is, like what Google does, is create some well-defined types. There's actually lots of well-defined types for things like GPS coordinates, things like that are more complicated data. There's lots for like date and time, things like that. So we can create protofiles that are standard definitions of things that we think are common. So waveforms, complex data, things like that. That's definitely something we can do, and then make sure we would use those internally for our APIs. And so we have a common waveform, a common frequency, data type, things like that would be great. Let's see. Yeah, so like streaming huge-ish data rates. So I mentioned what you can get if you're streaming over the network. You can get, if you have a 10 gigabit network, which are pretty cheap these days. The test that when I did the testing on 10 gigabit, I bought some $100 network cards. So nothing special. And I was able to get that greater than 1 gigabyte per second. Not gigabit, but gigabyte per second. So you can actually push a lot of data. See, a couple people voting for shipping with LabVIEW. Right now, it's we're using the VI package manager. Let's see, some back and forth on whether we should ship it. Let's see, any other questions? If not, again, feel free to, if you have questions in the future, you can also put the questions on the GitHub page. Probably if you have the question, someone else does. So if we answer it on the GitHub, that's just also answering it for someone else. So please participate. We would love to see that happen, and then also give us some more, ideas of like, is the open source model something that people are very interested in or not? So If there's no other questions, again, thanks very much for attending. I appreciate it.